So let me first thank the organizers for inviting me and well, allowing me to come despite that I turned down the first invitation, since I planned to go to Berkeley. But then at some point I found out that Newton Institute should be better than MSRI.
This makes you very popular, yeah.
This makes me okay. Always makes me popular because, well, the talk, actually this is the second thing to apologize. The talk doesn't have much kinetic in it. Well, I tried to derive the models I use from kinetic models, but so far didn't really succeed without cheating. So it's more mean field equations than kinetic stuff. So this is joint work, I should mention, with all these guys who are all here. And Bärbel was involved in everything. Then Marco and Jan were involved in a first paper. And Marie was also involved now in a second paper. We are dealing with applications to channel transport. So I start with some motivations and some applications. So this is where I show the nice images somehow. Then I will go to some modeling aspects and do some analysis, which actually turned out to be much harder than I expected originally. And then in the end I will give some outlook and things that are still open. So what is the motivation? If you look into real life processes, and this is the good position I have, since actually I'm only a part-time analyst. My main profession is to do mathematical imaging. So I get a lot of images from medicine and biology, and I look into a lot of transport diffusion processes. And if you look into those, then they basically combine these basic things, always with, or in many cases with size exclusions. And in many applications, really important that you have things of finite size. And as far as, well, I know up to a few months ago in the literature, you basically found continuum models with some kind of reasonable size exclusion only for one type of species. But of course, in the reality, this is much more heterogeneous. So for example, if you look into cell migration, this is a movie of the embryo development of a zebrafish from Eris Russ lab in Münster. What you see there is immediately, they also have labeled this by fluorescence. You immediately see you have two kinds of cells. I hope you can see it with the lighting here. I don't know if I can turn down that lamp. That would be probably not. Well, I hope you can see it reasonably, otherwise. Okay, let's make the interesting experiment of Peter trying to turn on the light. Okay, anyway, what you can see here is at least you have these kinds of germ cells and other cell nuclei. That was not an improvement. Anyway, okay. Now you maybe can see something now. So you see immediately there are two kinds of cells here, and you immediately see these things happen at pretty high densities. So it's really important that you model that they don't have size 0. Okay, another thing that we are dealing with a lot is the transport of ions, and nowadays also other molecules, through nanopores and biological ion channels. So there is also a lot of important effects that you can only deal with if you treat the finite size. And also you see in these processes you have always at least two different species. You have always one positively charged and one negatively charged. Otherwise the whole thing is somehow blowing up, because you cannot guarantee charge neutrality on both sides of the pores. And then you get troubles with the biology. So you immediately see that you have to model at least two species. Usually you have to model much more in these cases. Okay, and then the third thing is, well, something which is actually quite tragic, which was in the German news all summer. So modeling of human crowd dynamics. This is the tragic example from Duisburg, where they had actually only one entrance, which was also the way to leave. So they had two different kinds, at least if you would like to model this, there are two different kinds of people, one going out, one going in. Or you could look at some train station. This is maybe to make something else. Here you see you have many different kinds of people. They all head to different trains, so they all somehow are driven by different velocities in different directions. Okay. So if you look into the microscopic modeling, what people are doing, then basically you have two paradigms that you find. One is a purely force-based model, so you write down Newton's equations of motion, and then you introduce something like a hard core potential or Lennard-Jones potential to model that they cannot come together too closely, so something which drives them apart or which stops the motion if they get closer than somehow the sum of their sizes. This is a bit hard to treat in a macroscopic limit because you have these singular potentials, these singular interactions, and it's not completely clear what is the right macroscopic limit. I don't know any rigorous derivation of something reasonable. The other thing which, well, works a bit easier maybe is if you directly look into a lattice-based somehow jump exclusion process. So you just do basically random walks. Maybe you have biased random walks. If you have something like chemotaxis or if you have electric fields, you can incorporate this very nicely. But then you just, in the jump rates of your random walk to the next site, you just include that this site, in order to go there, it should be empty. So this modifies the jump probability. And there you can do a bit more. Okay, this is what I just said. You can include everything you want. And it's very simple to get a continuum equation if you make it very simple kind of closure relation. So instead of looking at the next side and looking whether it's really empty, you modify the transition probability by the probability that this site is empty. So this is kind of already of a mean field closure that you do, and this is some trick that is hidden actually in many papers. Then you get immediately a macroscopic, so if you do it for one species, you get immediately a macroscopic Fokker-Planck equation, and the only change, surprisingly, to the usual Fokker-Planck equation is this term. Well, this is not too surprising. So rho is the density or the probability. If you think of the density, then you have scaled it such that the maximal density is 1. And you somehow change the mobility from the linear mobility in rho to make it a degenerate mobility, which saturates if you reach the maximum density. Interestingly, and this is at the first glance a bit confusing, is the diffusion coefficient is not changed. So this is still linear diffusion. There is no 1 minus rho appearing here. You can do the analysis and you will immediately see it comes out like this. My only vague explanation is that at the macroscopic level, you basically, if they move randomly, you don't see whether there was size exclusion or not. If you only have one species, then you cannot, at the macroscopic model, you cannot distinguish whether these particles have stayed at their place because of the size exclusion or whether they have actually moved and changed places. It will give the same macroscopic density. Only if you have a biased motion, something will come up, and this is this term which comes here. Okay. And this model was actually, well, got quite popular in particular for chemotaxis, because in chemotaxis you have this blow-up trouble, and if you include size exclusion, then you would get something with global existence. So these are these models by Thomas Hillen and Kevin Painter in the early 2000s. And actually, if you don't make this closure assumption, if you really make a reasonable, rigorous random walk model at the microscale and do a rigorous limit, this was done in a different, actually with a different emphasis by Giacomin and Leibowitz. They didn't talk about particles and size exclusion, but basically what they did in their model from the asymmetric exclusion process to the continuum limit, they actually made this procedure rigorous. And then this model afterwards, particularly for chemotaxis, was pretty well analyzed and frequently used. For example, you get very interesting dynamics there. Jasmin Dolak and Christian have done interesting work on clusters forming in 1D. We have later generalized this to characterize the dynamics of such clusters of particles in multi-dimensions. And that's also quite interesting, an overview paper by these Australian guys. They discuss some issues. They discuss also a bit this paradox from a very also applied point of view, this paradox with the linear diffusion and the nonlinear mobility, and also the issues that you get in practice when you try to estimate diffusion coefficients from trajectory data. So this is interesting also if you do, like me, if you do imaging of cell trajectories and you like to identify what is the macroscopic diffusion coefficients, you have to be careful with this. Okay, and they also did some nice simulations. So here this is a pure random walk model starting from a density here, and then they also did a biased random walk, let the particles go to the right, and then they compared averages of the random walk simulations, which are the densities here, with the continuum simulation, and you see this has in all cases pretty good agreement, so it makes sense that you use this kind of continuum models to describe such situations. Okay, so what happens with multiple species? It's not really any way difficult to derive that model. Surprisingly, it seems that until 2 years ago, nobody has looked at multiple species. As far as I know, Marie Wolfram's thesis includes the first mentioning of such a model. And also surprisingly, within not even 1 year, basically 3 papers with 3 different motivations basically appeared for, and they basically derived the same model. So these guys, Simpson again, they have in mind in particular modelings of crowds and swarms. We had in mind modeling of ion channels, and Painter had a model in mind where he was thinking of differential chemotaxis. He has an additional term eventually because he's also sometimes allowing cells to switch places by an active pulling mechanism. So what you see in the basic model, you get continuum equations for each of the concentrations. And now what you see is you get again what you expect. So if rho is the total concentration, you get a change in the mobility here. So Wi would be some potential acting on the I species. Okay. I'll try this. So Wi is some potential acting on the E species. So this looks like in the one species model, except that already here you get some coupling. But what is again interesting now is in the diffusion something is changing. So in the one particle model, in the one type of particles, you got linear diffusion. Now you get 2 terms in the diffusion. You get 1 minus rho times the gradient of the density of the E species plus density of the E species times gradient of rho. So and what you see again, this is consistent of course with the one species model. If you only have one species, then Ci is equal to rho, and these 2 terms will cancel, so you only stay with the linear diffusion. So this is kind of interesting because originally we thought, okay, when we go to multiple species, nothing will really happen. We can just work with these models as we did. But here somehow the degeneracy pops up much stronger, and it really creates later troubles also in the analysis. And what you also see, you could write this differently. Actually, you could think of a microscopic model where you have 3 kinds of species, or n plus 1 kinds of species if you want to number them. And the n plus 1 kind are just the empty sites. And the density of the empty sites is of course 1 minus rho. So what you see here is basically you have a gain term, which is 1 minus rho gradient Ci. And this term is a bit hidden. This actually is minus the gradient of 1 minus rho. So the density of the empty ones. So this is a loss terms of losing a site to an empty site. And this is actually what is happening here. And this gets a bit clearer if you consider active change of place between 2 particles as Painter does, because then you get all these kinds of terms, Cj gradient Ci minus Ci gradient Cj in your model. Okay, so let's do it for 2 kinds of species. Like in the first movies, we have red ones, we have blue ones, and we call them their densities R and B. And the total density is then R plus B, and we scale, make the time scaling so that the first diffusion coefficient equals 1. So we end up with a model like this. And we see also here, well, it's not completely obvious, but it's a simple computation. You see that if you have a diffusion, if both diffusion coefficients are equal, d equals 1, then basically again the diffusion is dominated for the total density is dominated by linear diffusion. So if you add these two equations, then all the nonlinear terms basically drop out if d is equal to 1, and the diffusion part is d rho dt is equal to Laplacian of rho, and then you get some modifications from the drift. But if d is not equal to 1, the dynamics gets much more interesting and gets really hard to analyze this model also. And also, if you have large convective terms like this, turns out it gets really hard to do reasonable numerics also on this and to get stable simulations of the patterns that can appear here. Okay, just one remark, since everybody is doing gradient flows. This is a pretty nice example of a gradient flow. You can write it as a gradient flow with a diagonal mobility. Mobility is again modified like before with a 1 minus rho factor compared to the linear mobility. And you see again also in the entropy is not much happening. You have the usual, there's a factor here that should be there, but anyway there should be a constant here in front. But you have a sum of the usual ideal Boltzmann type entropies, and here you see again that you have actually a third kind of species because you have also the 1 minus rho log 1 minus rho, so you have also somehow the entropy for the free sides, and then you have the potential terms. And you can compute a nice entropy dissipation, of course, once you have identified the entropy and the gradient flow structure. You get an entropy dissipation like this. And you can also put some kind of transformation to entropy variables, which is not, well, it is quite interesting also in particular if you want to get equilibrium solutions or things like this, because in equilibrium these entropy variables are just constant. You can easily check that. Okay, so if you want to compute equilibrium, you get some formula like this. It's also not too surprising. You see immediately you don't have the usual Boltzmann statistic, but you have something which in semiconductors you would call a Fermi-Dirac statistics, and you see immediately that all the concentrations are less or equal than 1. And you have the constant entropy variables which you have to determine from the mass of the two species. At least if you use natural boundary conditions, then the mass is conserved. So this is a typical simulation. Put the reds on the left, most of the blues on the right, and you see, well, it's diffused. So this is only diffusion, there's no potential. You see it happens what should happen in diffusion. They equilibrate, go to a constant state. Not too surprising, it goes pretty fast, so maybe it's still exponential. Okay, what happens if you want to analyze this? Even if you don't have a potential, you would think, okay, this is a very simple exercise that you give to a student and he does it very easily. It turns out this is not the case. The trouble that you have is you have this double degeneracy, so at density equals 0 and density equals 1. Well, usually if you do this for one equation, it's easy to avoid the troubles because you use a maximum principle. Okay, now you have a system of two equations, so there is no maximum principle left. So you cannot use this kind of techniques. The only thing that from some kind of maximum principle you can deduce is that you have lower and upper bounds. So of course densities stay between 0 and 1 if you scale like I do. What is also not nice is you kind of get, since you have a diffusion model, you get the coupling in the highest order terms. So there's nothing like, if you would think isolating lower order terms and applying like something like Schauder fixed point theorem, there is not much hope to do it. And the other thing that you would try, of course, is kind of do some natural linearization. So if you think of this model, you might want to think, okay, I freeze the diffusion coefficient and then I get a nonlinear cross-diffusion model and then I work on this and then try to prove some fixed point argument. Also, this is hopeless because these linearized cross-diffusion models, if you linearize around some R and B, has absolutely no structure. So there's nothing in there. You cannot even show reasonable positive definiteness in these kinds of variables. Whoops. Okay. So what do we do in order to show at least that there exists a solution? Okay, we got very modest when dealing with this. We started and tried to prove everything, tried to do gradient flow arguments and all this in a very general way. And after some time, we realized it's a really hard problem. We have to study just to prove some existence of weak solutions, which is a hard trouble. Okay, what is nice if you transform this system to entropy variables, since you have this diagonal mobility, the spatial differential operator becomes diagonal in the entropy variables. This is why all arguments that you do on stationary solutions are pretty easy if you transform to entropy variables. Also, if you have crazy boundary conditions or if you have some interactions, it's not really difficult to prove anything about stationary solutions. However, what happens, of course, in the time-dependent case, you get a coupling in the time derivative. So you somehow remodel your system. Instead of having the coupling in the spatial derivatives, have the cross-diffusion, you get a coupling in the time derivatives. What is nice is this coupling is much nicer structured because it is symmetric in particular, and you can show that this matrix A, B, B, C, if you write down the A's, the B's, and the C, they are a bit lengthy, so I avoid that. But if you write that down, then this matrix at least is positive semi-definite. So there is some hope to freeze these coefficients. And the A and the B are also positive or at least non-negative. So there is also some hope to freeze the A and the B and to get something on there. Okay, and this is what we tried to do in order to have everything positive and not non-negative. We just add basically an epsilon to everything. So we add an epsilon to this A and B, and we add an epsilon to this A and C. So we get this matrix positive definite and the diffusion coefficients really positive. And you can see that this modification still leaves you an entropy. You can write the entropy in the dual variables. So this gives a dual, a functional, and you get additional terms from this epsilon linearization, which are just quadratic. Okay. Then to start some existence theorem, we do a Galerkin approximation in a finite dimensional space. This is pretty obvious then, as long as the epsilon is positive. Then we send the n to infinity, which is also okay because we still have the positive epsilon. What we use there is an entropy dissipation, but interestingly not in the original variables, again in the dual variables. So the relative entropies then also needs to be changed. You can figure that out easily. Usually you take the relative entropy of your solution with respect to the equilibrium solution. So you would have here the derivative of the equilibrium solution, not of the time-dependent solution. Here you have to change this role since you work on the dual somehow. You see it from an optimization point of view. And then you figure out easily there is a nice entropy dissipation. And in particular, you have the entropy dissipation, which has gradients of u squared and gradients of v squared. And since you have added an epsilon, you get h1 bounds from the entropy dissipation. This is the main thing you need. So you get uniform bounds in n, but still not in epsilon. But at least you can pass to the limit from this Galerkin technique. Okay, what is then hard? The second step is you need to go with the epsilon to 0. And then you lose, of course, the uniform gradient bounds that you would have from here. It turns out if you write out the entropy dissipation now in the original variables, what you always get is a nice bound on rho, also no matter what the diffusion coefficient is. So you get somehow what you would have as an entropy dissipation for linear diffusion. And then you get something which is a bit less attractive. You get almost a nice usual entropy dissipation for the individual densities, but they're always multiplied with the 1 minus rho. So you always get in trouble when rho could be equal to 1. Okay, so at least we know something from this, and we get a lot of information about 1 minus rho, and actually even about square root of 1 minus rho. And we get an information, if we take the square root here, this is square root of 1 minus rho times square root of r. Okay, so you can at least, and then you have of course some L infinity bounds, so you can extract some weakly convergent sequences. the only trouble that remains is how you would pass in the limit to this nonlinear term in the diffusion. So in the diffusion you have the divergence of this quadratic term somehow. So what we did in the end is we were rewriting this in terms of square root of 1 minus rho and square root of 1 minus rho times r, which sounds crazy at the first place, but if you look at the entropy, I mean, these are exactly the things where we have bounds on. Okay, and then we use all kinds of usual arguments to pass to the limit in these two terms, and then we can pass to the limit in the equation and get a weak solution. So you see, it's quite a long story for quite an innocent model. I mean, you have what you have. If you forget the potentials for the moment, you have only diffusion, and you even avoid high concentrations. So this should be the most simple model that you could have, but still there is not much in the analysis that we can say. Next question, uniqueness. Basically there is no answer, so it's a question for anybody who needs a hard question, uniqueness for this model. The only result that we have is basically if we have initial values close to equilibrium, but also very strongly in an H2 sense, okay, then we can apply an implicit function theorem and we can get local uniqueness around equilibrium. Well, this is reasonable, but still it's also pretty hard since we need H2 closeness, not even H1 closeness. So it's not even in a weak sense close. Okay, the next thing is large time behavior. I've shown you this simple simulation. What you get is at least you have the entropy dissipation, so this is decreasing, so you can show that this relative entropy as usual goes to 0. And then what is nice is since we can prove the uniqueness of the equilibrium and show this is the unique minimizer of the entropy, then we use a Chishak-Kullback inequality, and we get in the end, so from the convergence of the entropy we get L1 convergence to the equilibrium. But without any speed, we cannot say anything about the convergence speed, and we cannot get even rate if you have only diffusion and no potential. So another question for somebody who looks for interesting challenges. Okay, we can look for some limits in the diffusion coefficients. So if both diffusion coefficients are equal, this is what I already said at the beginning. If we have no potentials, then we have linear diffusion for the total sum. This is obvious, since if the diffusion coefficients are equal and we have no potentials, then there is no way to distinguish these two species, so we can just write linear diffusion for the whole thing. Another thing which is interesting is if one of them is diffusing much faster than the other, but we stay on the diffusion scale of the slower one, we can also look at this limit. It turns out that we end up, so in this case B is diffusing fast, R is diffusing slow, and we can explicitly compute an effective diffusion coefficient, which gives again linear diffusion for R. And we can compute this reduced effective diffusion coefficient. You can easily figure out this is less than 1. So this should also be a consistency kind of with a standard theory that you would make. Okay, so now if you want to go more towards application, you can ask various questions. This is already a bit kind of an outlook. So what you observe in these pedestrian models, that if you take a long corridor, you will have some kind of lane formation. So these are examples done by Armin Seyfried and this group in Jülich and Wuppertal. So what they do is they do quite artificial experiments. So they put the people also into red and blue clothes, which makes them easy to distinguish. One of them going left, one species going right, and you see there are some kinds of lanes forming depending also on the frequencies of the incoming pedestrian. Actually, we started to work on this since we wanted to do again image analysis on models like this, but not on models where you have pre-marked the people, but on real life observation movies, because when you want to test the models with such experiments, it's not completely fair because the people know in advance what's going on, so they don't probably behave as usual. Okay, so I had a hard time trying to model this. Well, not to model, but to compute. So actually, like 3 hours ago, I got the first parameter set where it really worked. So you see here you have the red's going right, left, the blue's going right. And you see here the plot of the density. So we have homogeneous, no, not homogeneous, but constant influx-outflux boundary conditions. We have a small perturbation of a constant initial state, and what you see is indeed, so the perturbation is such that the reds would be a bit higher here, and the blues would be a bit higher here. And indeed you see, so red is in the end color code for 1, blue is for 0. So you see all the reds would go on the right, all the blues, well, depending what, they go to this, so both of them go to the right, which is not the UK sense of going. So my perturbation was, of course, the Central European one. But you see, indeed, this is, to my knowledge, is the first time that you observe something like lane formation in a continuum model. So all these people doing pedestrian models, they would never have believed this. Well, I still have to, since I didn't present this to the really applied guys, I still have a hard time discussing this. But as an outlook, I think it's quite interesting to see that something like this can happen. And we can also do it, I erased somehow an important slide, I guess. Yeah, here. So what we also can do is, for this example, this was not constructed arbitrarily. It was constructed since Bärbel had a hard time doing linear stability analysis. So you can start with a constant solution and try to figure out linear stability or linear instability of the constant solution. And in some parameter range, indeed, it happens that it becomes linearly unstable. And this now corresponds the first time also to my numerics. So we have to figure out a bit more what's happening with the nonlinear instability later. Okay, another thing that we're dealing with, of course, is ion channels. There, of course, you deal with electric stuff, so you look into plots of the current. So if you do, of course, a current close to equilibrium for a standard model that you would use, which would be like drift diffusion for semiconductors, and you plot this versus concentration, this is always increasing. If it's close to equilibrium, then it's always linearly increasing, no matter how large the concentration is. So even if you model, so this was a 2D numerical computation on a real channel geometry. And if you, of course, now put this model with the size exclusion, then the current will saturate at some point. And of course, if the channel is completely filled, it goes down to 0 since there is just a jam happening. So this will also be interesting to look more into this kind of current pattern and maybe some other effects that you have there. Okay, I had some challenges, some analytical challenges also already in my talk. There are also some interesting modeling challenges. So if you start this lattice-based modeling, then immediately you somehow induce that all the species have the same size, which is not true in reality. In particular for ion channels, it's very important that you have large ions and small ions. So you have to go away from the lattice-based model to include the size of the species into the model. We can roughly do it again once we have derived this model. We can insert the size by rule of thumb into the continuum model, but there is no nice derivation of this. And this is, of course, related to the last challenge. The question is, can you derive something like this from Newton equations of motion with singular forces in an overdamped limit, which I think is not a trivial problem if you want to do it in this kind of limit. So you don't have the, so it's, you have the situation where n times the volume of the particles is going to a constant, so it's like in the Nskog equation for dense gases somehow. Okay, so this was everything I wanted to say, and we've quite some stuff also, further information if you're interested. Thanks.
Are there questions, comments?
In the lane formation models, how would you see sort of comparisons to mean field games?
I'm not sure about mean field games. I mean, if you do mean field games for a T reasonably large, you would assume that you know what the others are doing for a long time in advance. I'm not sure if this is really realistic. I mean,
no, but as you know, lane formation has been generated in mean field models, right? At least it's an experiment.
She didn't tell me yet, so I haven't seen it yet. So the principle could be very similar. It could give some similar equations also in the end. But I would only accept the mean field game approach if the T that you use is pretty small. And then you might want to develop these mean field game equations around t equals 0 or t equals the current time. And they might give something similar. It would be interesting to look more into that.
Yeah, in the pedestrian simulation you've shown, it seems that the pedestrians are blocked at the end.
Yes, they do.
So is it something realistic?
Well, it happens that, well, for high density it happens that they get blocked in the end. And I can't tell you much about what happens under what situations, because this is one of the few.
Obviously, in your experiment, it did not happen. They seem to go through, so
yes.
It's kind of.
Now we have to check what is the densities they have and the density we have, because the density gets very high here. It gets really almost 1 here. I mean, I could say, if I want to exaggerate, I could say the Duisburg experiment, it happened. So they couldn't pass again. So there the density was extremely high somehow. So I'm not sure what's happening. We have to play much more. I just can't tell you a reasonable answer, because I don't have enough cases where I can so far compute this where the numeric stays stable. So I assume that if you do it for a different set of densities and parameters, it could be that there is no jam. It depends also on the.
Do you get unjam situations with this simulation, or do you always get jam?
Basically, the only I get a lot of situations where the constant density is stable. Okay, there's a lot of parameters I can compute where I get a constant density of something like, I don't know, 0.4 or something everywhere. And then, of course, there is no jam. If you look at the flux, there is nice flux. So far, this is the only one where I get very strong lane formation between the two, and then I got the jam. I don't have an example where I get lane formation without the jam in the end. But I think crucially depends what kind of boundary conditions you put here. I mean, this is really, the boundary conditions here are really, again, like in the old Lyon's saying, this is made by the devil, so you can spend a lot of time trying to figure out what boundary conditions to put, what are the reasonable values. You see also here you have some kind of boundary layer here. So I'm not sure. I would expect that for reasonable settings of boundary conditions I get something without the jam. And also if I vary the size of the channel, things like this. But I just can give you a definite answer.
What generates the asymmetry in the solution? You have initial condition which is asymmetric, or what?
It's an initial condition which is slightly asymmetric.
So that's basically determined by...
This is consistent with the linear stability analysis. So we know in this case, if you put this perturbation, the constant state, the constant density is linearly unstable, so it must go away. And then it really happens that we get this strong. In the end, it must be a nonlinear instability also.
What happens if you start with symmetrical?
We cannot hear.
You have to be very careful. If you do numerics, it has to fit to the grid. But it should. Well, I mean, I would expect that at some point you get some numerical perturbation, and then it goes to the linear instability. I mean, it's always hard to compute the case which you only get without any perturbation. If I construct the scheme which is completely symmetric, so they should stay like this. But yeah, and as I said, I have many examples where it goes back to the from a perturbation, it goes back to the constant density. So there are many parameter sets I tried where I get this behavior.